The device you're watching this on right now is performing billions upon billions of calculations every single second. It really feels like magic, but it's not. It's engineering. Today, we're going to pull back that curtain and see how your computer's brain, the CPU, actually works.
It's a question that's always kind of blown my mind. I mean, you see these tiny, intricate little squares of silicon, and people tell you they're the grains of our phones and laptops. But how in the world do you get from, well, a piece of sand to something that can run a web browser, a video editor, and the most demanding video games, all at once? Well, let's find out.
Okay, so let's dive right in. To really get how a CPU works, we've got to go back, way back, to the 1940s and a brilliant guy named John von Neumann. He came up with this really simple, rhythmic process that is, believe it or not, at the core of every single computer today, from your smartwatch to a massive supercomputer. It's the foundational heartbeat of all modern computing. And here is that heartbeat. It's a simple four-step dance. First, the CPU fetches an instruction from memory. Think of it like grabbing the next item on its to-do list. Then, it decodes that instruction. Basically, it figures out what it's being asked to do. Next up is the execute stage, where it does the actual math, the actual work. And finally, it writes back the result. That's it. Fetch, decode, execute, write back. With every single tick of the computer's internal clock, this cycle just repeats over and over and over again. Now, that four-step process, it's elegant, it's simple, but it has one massive problem. On its own, it's just way too slow. Modern apps, games, streaming video, everything we love about our devices demands a speed that this simple little cycle just can't deliver. So how do we get from that steady, simple beat to the absolutely blistering pace we need? Well, this is the scale of the challenge we're talking about. A modern CPU can run at over 5 gigahertz. That means it can perform one of those cycle steps more than 5 billion times every single second. Seriously, just take a moment and try to wrap your head around that number. It's absolutely mind-boggling.
And just to put that in perspective, 1 gigahertz is a billion cycles per second. So at 5 gigahertz, each of those 4 stages we talked about, fetch, decode, execute, write back, has to happen in just 5 billionths of a second. That is literally faster than the blink of an eye. Heck, it's faster than a lightning strike. It's an almost unimaginable speed.
So this is the real puzzle, right? How did engineers take that beautifully simple but kind of slow four-step loop and turn it into the absolute powerhouse that's sitting in your device right now? The answer isn't one single thing, but a series of incredibly clever engineering breakthroughs that we're about to explore.
The very first major leap forward is a concept called pipelining. And honestly, the best way to think about it is with an idea we're all familiar with, the assembly line. It completely revolutionized manufacturing, and it turns out it did the exact same thing for computing. So, in the old days, with sequential execution, one instruction would go through all 4 stages: fetch, decode, execute, and write back. And only when it was completely done could the next one even begin. It's kind of like one person building a whole car from scratch. It's super inefficient. But with pipelined execution, it's totally different. While one instruction is being executed, the next one is being decoded, and a third is being fetched, all at the same time. It's this continuous flow of work, just like a real assembly line.
And this quote really just nails the comparison. Just like Henry Ford figured out he could build cars way faster by breaking the process down into smaller, specialized stages, CPU designers did the exact same thing with that 4-step instruction cycle.
And they didn't just stop at 4 stages. Not even close. A modern microprocessor pipeline isn't 4 steps anymore. It can be 15, 20, or even more distinct stages. And the more stages you have, the less work each one has to do, which means each stage can run incredibly, incredibly fast.
Now, to manage all this complexity, engineers usually split the pipeline into 2 main parts. You've got the front end, which is kind of like the manager of the assembly line. Its job is to fetch and decode instructions, making sure the right parts get to the right places. And then you have the back end, which is the team of specialized workers actually doing the heavy lifting, executing the instructions and writing back the results. So now we have this incredibly fast data assembly line, right? But as any good engineer will tell you, solving one problem often creates a brand new one. What happens if there's a little hiccup on our superfast line? A single delay could cause the whole thing to grind to a halt. So engineers needed to find a smarter way for the CPU to work. And the biggest headache of them all is something called a branch instruction. Imagine you're flying down a highway at top speed, and suddenly you see a fork in the road up ahead. You have to decide instantly which path to take. That's exactly what a branch instruction is for a program, and it's a huge problem for our high-speed assembly line. So here's the big dilemma. When the CPU's front end sees one of these forks in the road coming up, what should it do? It could just slam on the brakes, stop the entire pipeline, and wait for the back end to figure out which is the right path to take. Now that's the safe option, but it's terribly slow, and it completely kills the whole benefit of the pipeline. Or it could take a risk. It could try to guess.
And that risky choice leads us to the next incredible innovation, speculative execution. This is where the CPU basically becomes a fortune teller. Instead of waiting, it makes a highly educated guess about which way the program is going to go, and it speculatively starts fetching and executing instructions down that predicted path before it even knows if it's right. It's like the CPU is constantly playing a high-stakes game of what if. So how good is it at guessing? Well, this quote says it all. Modern CPUs have become so ridiculously good at learning from past behavior that their branch predictors can seem almost clairvoyant. They guess right over 90% of the time. And when they guess right, the time savings are massive. If they guess wrong, no big deal. They just flush the incorrect work and start over on the right path. The penalty for being wrong is tiny compared to the huge gains from being right so often.
Okay, so now we've solved the fork in the road problem. We have instructions flowing into the back end at this incredible rate. But that just creates another bottleneck. What if one instruction is stuck, waiting for some data, while a bunch of others are ready to go? The source material gives us this fantastic analogy. Think about running a busy restaurant kitchen. A good restaurant doesn't make every single dish in the exact order the waiter took them, right? The kitchen gets started on some quick appetizers while the more complex main courses are still being prepped. A CPU does the exact same thing with something called out-of-order execution. The back end looks at a whole batch of upcoming instructions, and, like a master chef, it reorders them on the fly to keep all of its different parts busy. It executes instructions as soon as they're ready, not strictly in the order the programmer originally wrote them.
So, check this out. Instructions 1, 3, and 5 here don't depend on anything else, so the CPU can just start working on all of them at once, in parallel. But look at instruction 2. It needs the result from instruction 1 before it can do its job, so it has to wait in this little holding area called the scheduler. By going ahead and processing 3 and 5 while 2 is waiting, the CPU avoids wasting any precious time and just maximizes its efficiency. And don't worry, it's smart enough to put all the results back in the correct order before it's finished.
Okay, there's one final absolutely crucial piece to this whole speed puzzle. All these clever tricks, pipelining, predicting, reordering, they're all useless if the CPU is sitting around starved for instructions and data. And this chart shows you why that's a very real danger. Fetching something from the CPU's own super-fast local memory, its cache, takes maybe 1 or 2 clock cycles. But fetching that exact same instruction from your computer's main memory, the RAM, can take around 200 cycles. That's like the difference between grabbing a screwdriver out of your pocket versus having to drive all the way to the hardware store to get it. It's a massive, massive performance killer.
So, as you can probably tell by now, designing a modern CPU isn't just a science. It's really an art form. It's this constant, delicate balancing act between how deep your pipeline is, how accurate your predictions are, how many things you can execute at once, and how big your cache is. Every single design choice is a trade-off, a creative solution to squeeze out every last drop of performance. And the progress that's been made is it's nothing short of a miracle. This quote really captures that feeling. I mean, we went from room-sized computers made of vacuum tubes to packing billions of clairvoyant, out-of-order transistors onto a chip the size of your thumbnail. The innovation has been absolutely relentless. And the best part? We're really just getting started. And that leaves us with one final thought. These processors aren't just getting faster anymore. They're getting smarter. They predict, they reorder, they learn from their mistakes. As this trend continues, what new frontiers in artificial intelligence, in science, in medicine, and just in our everyday lives will these ever more complex brains unlock for us? What will you do with all that power? Now that's what's truly exciting to think about. Thanks for watching.